Good morning, good afternoon, and good evening, and thanks for joining the session on Inside BigQuery BI Engine. I'm Vinay Balasubramaniam. I'm a product manager on BigQuery. I'm also joined by Moshe Pasumaski, who is a principal engineer on BigQuery. So in today's session, I'm going to provide an overview of BI Engine, why we built it, what is a key customer use case, what problem are we solving. A good bulk of this talk is going to focus on how BI Engine works internally, the core architecture, and we'll have some demos at the end demonstrating BI Engine's high concurrency use case. And I'll be joined by Kevin Marr, who's a product manager on Looker, to talk about the BI Engine Looker use case. So let's get started. Doing business intelligence on big data is challenging, and we've heard it from our customers. Customers who are using traditional BI tools have to manage data marts around the data warehouse, manage complex ETL pipelines to move the data into the data marts to pre-aggregate the data, and then connect the BI tools into that. This adds a lot more complexity to the whole data flow. Secondly, customers today want more real-time access to their data for decision-making, which is done fast. Traditional BI tools require you to extract the data, thereby introducing a lot of staleness in your overall data platform. And lastly, as organizations scale globally, they would like to give access to the data to a lot more users within the organization and also to their partners so that they can analyze this data. Now, this adds a lot of concurrency requirement to the data platform, and the BI tool needs to scale to support this higher concurrency. GCP provides a comprehensive set of services to manage the overall lifecycle of business intelligence. Starting from data collection, we have different connectors which connects to traditional software as a service endpoints like Salesforce, Marketo, but also to traditional databases which are on-prem or running on other clouds. Once the data is inside GCP, we provide different services for transforming this data. For example, you can use Cloud Data Flow to analyze data in a more real-time streaming fashion. Or you could use Cloud Data Fusion if you want to build traditional ETL pipelines. Or you could use Cloud Data Prep for managing Hadoop and Spark workloads. Once the data is transformed, it's available in BigQuery, which is our cloud-scale data warehouse. On top of BigQuery, you could use Cloud Data Catalog for metadata management, or you can also use Cloud Data Prep for data wrangling. There are multiple BI tools which can connect to BigQuery. Today, we have Looker, Data Studio, and Google Sheets as our first-party BI solutions, which connect to BigQuery through BigQuery API. But in addition, we have partner BI tools also connecting to that. BigQuery BI Engine was built to become the acceleration layer between the BI tools such as Looker and BigQuery. The whole vision of BigQuery BI Engine is to democratize BI by enabling data and business analysts to perform interactive analysis on the data in real time. Traditional BI tools compromise between data freshness and speed. If you want data to be really fast, you have to extract the data. In this process, you lose the freshness and you end up doing BI on stale data. If you have to do BI on fresh data, it's not fast. Our vision for BigQuery BI Engine to not compromise between these two dimensions, to always provide fresh data fast. And there are three key value propositions for BigQuery BI Engine: sub-second queries, simplified architecture, and smart tuning. Let's go through each of them. So BigQuery BI Engine is a column-oriented dynamic in-memory execution engine with a vectorized runtime. It can scale horizontally. As you have more and more queries coming in, more concurrent query access, BigQuery BI Engine can replicate its data in memory to load balance all these requests, thereby supporting higher concurrency. And lastly, BigQuery BI Engine natively integrates with BigQuery streaming for real-time updates. So as data is being streamed, it's available instantly for BI Engine to aggregate the data and provide real-time access to data in your dashboards. Second value prop is simplifying architecture. BigQuery BI Engine is built directly over BigQuery storage system. So whether you're ingesting data through batch or streaming, the data is instantly available for BI Engine to analyze. This simplifies the overall architecture. You no longer need to extract or manage complex ETL pipelines to move your data from BigQuery into other subsystems. And, and today, BigQuery BI Engine is available for Data Studio, but what we're going to launch later this year is BigQuery BI Engine API, which is integrated directly into BigQuery API. This allows solutions like Looker and other BI tools to easily integrate with BI Engine without having to make any change. BigQuery BI Engine has inbuilt smart knobs built in. So just by creating a simple reservation in the UI, where you can pick a location and specify the size of your memory you need, BI Engine automatically takes care of which columns to use to query and cache it, and use that self-optimization mechanism to improve the query performance. And lastly, all of these heuristics about BigQuery BI Engine metrics, such as how much of the data is in memory, how much memory is being used, how much of data is query performance enhancements is coming from the memory tier versus how many of the queries fell back to BigQuery. All of this rich metrics is available in Stackdriver for you to analyze. So that was a quick overview of how BigQuery BI Engine works. Now let me hand it off to Moshe, who's going to walk us through how it works internally and he will go into a lot more details about this.
Hello, my name is Moshe Posumansky and I'm engineer on BigQuery, and I'm going to talk about how BI Engine works internally. So in order to understand it, first let's take a look at BigQuery architecture. So this is the classic BigQuery architecture picture, and we see that there are three main pieces. On the right we have compute, all the worker nodes. On the left we have storage, that's where BigQuery stores all the data, and in between we have shuffle network layer. So let's see how BI Engine fits into this architecture. So we see that it fits very naturally. The only thing that we changed about architecture, we added another type of workers, stateful BI Engine workers. Now, if that was such a small change and everything else stays the same, storage system is the same, as Vinay said, shuffle and network is the same, so how do we get such a great performance out of BI Engine? And this is exactly what I'm going to talk today. In order to understand how we could compress all the times almost to zero, we'll take a look at each one of those three components. Okay, we have compute, storage, and network. Let's start with storage, because it's the simplest one. Right, so BI Engine works by virtue of putting its data into memory. But of course it's more complex than that, right? If we could put the entire tables, all the tables that you have into memory, it would have been easier. But obviously tables are much, much bigger than the memory that we have. So what happens is BI Engine doesn't put the entire table into memory, it puts pieces of it. Remember that BigQuery is a columnar system. So BI Engine has the luxury of putting just the individual columns, the one that gets used. Moreover, it doesn't have to put entire column, it can put parts of it. If the table is partitioned, it can put only the recent partitions. But even if the table is not partitioned, BI Engine can take pieces of the table or pieces of single partition, the one that actually gets used, and put it into memory. Again, if the table is much bigger than the memory, then BI Engine has to figure out what is used, what is not used, what is beneficial to put memory, and so on. You don't have to worry about any of it. But even if all of the data were to fit into memory, there are still more complications. Suppose there are a lot of users connecting to the same table at the same time, very high QPS, and we're going to see demo of it at the end. And then maybe single worker will not be able to handle all this traffic. So BI Engine will decide to actually replicate the same data into multiple workers, even if it fits into their memory. So, pretty complex system. Again, you don't have to worry about it, but you as a user have control. What kind of control you have? Let's take a look. You have all the metrics exposed on the Stackdriver. And here in this chart we see an interesting picture how two of them interact. So we see two lines. One is how much memory you're paying for, and another line, how much memory you are using. So at the beginning, you are paying for 2 gigabytes, but using less than 1. So it's waste of money, so you can say, you know what, let's reduce our memory commitment to 1 gigabyte. But, of course, as the luck has it, right after it happened, the usage start to grow, and you see that memory usage start bumping into the limit. So you say, you know what, now we're using much more, let's go up to 3 gigabytes. And then, usage goes up, stabilizes at some point. So again, you as user, you have this trade-off, and you make this decision, how much money you pay versus how much performance you get. Okay, so that was storage. Let's take a look at the second component. And second component of our architecture is compute. Basically, we're going to see how BI Engine now going to put CPU usage and time it takes to run computations close to zero. It turns out that to build a runtime which works with memory resident data is very different from building runtime working with disk-based data. So the traditional model that all the databases have been doing since 70s is called row-based processing, where query engine builds kind of this graph of operators which take one row of data at a time, pass it through operators, and so on. But within memory and columnar-based data, there is a much, much better model called column-based processing, because it's for column-based data. It's also called vectorized processing, because what happens is instead of taking one row at a time, it takes one column and block maybe 1,000 rows at a time and processes them in a tight loop. So this is pretty dramatic architectural change, and we ended up completely rewriting the entire runtime in BI Engine to be fast. But it was worth it. We'll see some results. So now what happens is by taking those 1,000 rows of one column at a time, do processing and pass to the other operator. Has many, many benefits. Now we get better cache locality. We're able to use some special processor instructions called SIMD instructions. We get very tight loops which can work very, very optimally. We get branch predictability and so on. So this is how we're optimizing CPU usage. But that's just one of the techniques. The other thing that we're doing is we're using many different encodings. So in this slide, I'm showing a couple of them, but we have about a dozen. So two very common encoding techniques are called, one is called dictionary encoding, and another one is called RLE, run length encoding. So basically, dictionary encoding works really well when you have column with very few distinct values in it. So instead of keeping those values, we just keep them in a dictionary and remember the indexes into this dictionary. It helps in a lot of different computations. For example, instead of evaluating expression over every value in the column, we just evaluate it over the dictionary once. Hopefully there are only a few values. In this example, only 3. And then remember the result and just apply the result. Likewise, we can take advantage of dictionary encoding in group by and aggregation calculations. RLE is also similar because run length encoding means you have the same value repeated many times together. So instead of recomputing expression every time we compute it once and apply to entire run. As I said, we have many more other more specialized encodings, but basically what I'm trying to say, BI Engine runtime is pretty sophisticated. That's why we had to rewrite it, to take advantage of all of this vectorized processing and different encoding to get great performance. Last component is network. How do we eliminate network? And this actually turns out to be pretty tricky and goes into the heart of the query planning. So since we have data in memory, we come up with pretty different query plans, and I'm going to illustrate it in a couple of examples. So first example is aggregation, very simple. So what you see here is query plan for the distributed aggregation in the regular BigQuery. What happens is, we have distributed processing, many workers, each one reads its own piece of data, does local aggregation, sends results over the network to do the final aggregation. Pretty straightforward. Let's take a look how this plan changes when we have BI Engine. Well, it looks, the picture looks exactly the same, but there is very important difference. We are no longer sending results of local aggregations over the network because our scheduler knows where each shard of data is located at which worker, so it can collocate processing in such a way that instead of distributed computation, we're doing parallel computation, and everything is aggregated in memory of the same worker, so have less network load. Let's take a look at a more sophisticated example of joins. So what you see here is BigQuery plan for broadcast join. It's a very typical type of join when you have very big fact table and small dimension table. So what BigQuery ends up doing is it takes this small dimension table and broadcasts it to all of the workers using network, of course. Now, how this plan looks like with BI Engine, it's right here on the right. So what BI Engine does, it says instead of doing broadcast and using network, we'll just keep the same small dimension table at every single worker. So every one of them can do local join and not use network at all. So there are many other techniques that we do in query planning, but all of them are tailored towards our knowledge where data is located and how we can take advantage of it. So now that we saw how we're using CPU, storage, and network, how we're optimizing all of them, let's take a look at a couple of demos, how it looks in real life. And our first demo is going to be demo of high concurrency and high QPS. So basically, we run a simulation of typical office which have many different workers, and let's say all of them, in order to do their job, need to look at some data, and they have some complex dashboards, and we said each dashboard can have 10, maybe 20 different visualizations, each one sending multiple queries. So imagine, 8 o'clock in the morning, all the workers come into office, all open their dashboards, each dashboard sends many different queries, all at the same time. What happens? So let's take a look at what happens by looking at stack driver charts. So what we see, initially we see maybe there are few workers coming in and we have 100 QPS, meaning 100 queries a second. So if each dashboard was sending 10 queries, it means 10 users at very same time open their dashboards. Okay? So we have 100 QPS, fine. Let's see what happens next. Next, the load increases to 1000 QPS. So maybe now we have 100 users sending 10 queries at exactly the same time. And now 2000 QPS. So, okay, so QPS goes up, but what is happening with the system? Maybe it's falling over. So in order to understand how BI Engine handles all this load, we're going to see to 3 lines at the bottom. But in fact, they're so small at the bottom that it's hard to see, so let's zoom into them. Those 3 lines represent latency of BI Engine. And they show 50th percentile, which is median, but in distributed system, tail latency is most interesting metric, so we're also looking at 95th percentile and 99th percentile. And what we see here is no matter how much QPS we're putting on a system, the latencies stay about the same. It actually stay pretty low. Right? The median is about 30 milliseconds, and 95th percentile is 90 milliseconds, and even 99th percentile, which is a tail, is still only about 140 milliseconds. So no matter how much load we're putting on the system, like 2000 QPS, it holds the same without degradation. Of course, it was possible because in this particular case, user paid enough money and bought enough reservation, but BI Engine was smart enough to figure out which data is queried, how to distribute it, how to handle the load. Okay, now I will be handing it off to Vinay to show the next demo. Thank you.
Thanks, Moshe. Now I'd like to invite Kevin Marr, who's a product manager in Looker, to talk about Looker's integration with BI Engine.
Hi, I'm Kevin, a product manager at Looker, and I'll be showing you Looker's integration with BigQuery's BI Engine. First, Looker is a modern data analytics platform that operates in database. This means that Looker does not ingest your source data. So when you load a report or visualization in Looker, a SQL query is being sent directly to your data warehouse. And as you can imagine, having a very fast data warehouse means that you'll get a very good experience in Looker. So I'm in Looker's Explore page, which allows business users to self-serve by exploring their data, building their own visualizations, and ultimately answering their own questions. The Explore page is powered by Looker's modeling layer called LookML, which provides an abstraction layer between your database schema and the business terms that your users are familiar with. All I have to do to build a query here is select dimensions and measures and add filters. Say I want to know the total revenue we've ever made in our fictitious e-commerce store. I can just click on the total sales measure and hit run. But behind the scenes, Looker has generated a query, a SQL query for me, and has sent that to BigQuery, in this case BI Engine, and has given me the answer, in this case $9.6 million. It's easy for me to add things like filters. Say that I want to look at this over some constrained time frame. I can click on filter. I can pick, any of these easy point and click options. I'll just pick, say, I don't know, April 2020. So starting on the 1st of April and ending on 1st of May. As I've done those interactions with the user interface, again, Looker is adapting the SQL to reflect what I want. And when I hit run, that SQL gets sent to BigQuery's BI Engine, and the result is posted here. Great. So in April 2020, my business made $441,000. Also, if I jump over to the BigQuery console, we can take a look at those queries, and you can just get a sense for how fast these queries really are. If I click on this, you can see that that query I just ran took only a quarter of a second. Now let's take it a step further, and maybe I want to create a visualization. Maybe I want to create a time series. I can do that just by adding the date dimension to my query, again, hitting run. Looker has adapted the SQL, and the result is displayed here in Looker's user interface. If I want to visualize it, I can just open up the visualization section where we have a myriad of viz types. In this case, Looker thinks that a line chart is the best based on my data, which I like. And I'll go ahead and save this to a dashboard. I have a nice little test dashboard I added. I'll save it there, and I'll pop that open in my other tab. I'll go ahead and refresh this dashboard just to rerun these queries. Again, we've turned off all caching on this demo just to show off the query speed in BI Engine. Looks like the dashboard's done rendering already. And at the bottom, I can see my new tile. I actually added two from a previous recording, but pretend it's just one. Dashboards in Looker are also designed to be heavily interactive. So say that, right now we're looking at just the data over Facebook. I can deselect that selection, and that'll cross-filter across all my other queries. Now I can see the data broadly across all the demographic profiles. I can also adjust filters directly in the top. That I want to look at this specifically in some city, say, San Francisco, where I live. I can start typing that in, and Looker will start offering suggestions based on my underlying data. So I can click that, rerun the dashboard, and see how this is trending just in San Francisco. Great, that's it. Thank you very much.
Thanks, Kevin. That was an exciting demo showcasing BI Engine with Looker. To conclude, we saw a great overview of what BI Engine does. We went into a lot of details on how BI Engine works. You can try BI Engine today. It's available with Data Studio as a GA product. But what's coming later this year is BI Engine SQL API, which expands BI Engine to other solution BI tools such as Looker and other partner tools. Thanks for watching this breakout session. Have a great conference.
you.